question that's
Oh, hell yeah.
asked
Oh, we're doing it right now.
Answer it.
We're doing it right now. And it's just a long question to answer because it's not a yes or no.
Yeah, but
It's-
just an example of a question that you would, like, something you would ask that would say like what would it be like?
We're getting there.
What percentage of weight loss?
Yes, that's the
Answer
question.
standard deviation. Or
That's the,
something like
that's
that.
the, you just asked it. Candace, you just asked it, right?
Yeah.
What percent of our sample data
And zeros in there too.
is within, and let's do a 1, 2, 3. This is, I mean, we're getting there. You've been very patient. I appreciate you waiting. Because it's been an hour and a half on the same data set. And I do appreciate the patience you guys are showing because it's like, okay, we're very slowly going through this, but there's a reason for that. There's an underlying truism that takes time to actually get to. So how about within one standard deviation, which would be in symbols x bar plus or minus s. So how many friends?
23.
There were 23? You get 23? Maybe you got different depending on if you included 23, 24, 25, 22, somewhere in that neighborhood. We'll go with 23, right? About 23 out of the 35, which as a fraction is going to be, is that 2/3, like 66, 67%?
I feel like that's a number we already used.
We already used, did we?
I feel like we did.
Did we? Maybe.
Pretty close, I think.
It was,
26 before and that was 75%.
65.
Oh!
Yeah, the 26
Gotcha.
is over
Good.
35.
Let's come back to that, if you would. Let's come back to that, friends. I want to come back to that. So, what percentage is this?
67.
66, 67, about 2/3, about 67%. Just keep that in the back of your mind for now. I love the fact, we were at 75% last time, right? Which was a couple different. When you have this small a data set, if you choose to include or not include a data point, you're going to change the percentage by like 3%. Because with 35 data points, each one is a sizable chunk of the data set. So that's why it seems like we're pretty close, because we actually are pretty close. Okay, how about within 2 standard deviations, which would be x bar plus or minus 2 s's. What do you got there? I'll do it too. We're recording, right? Yeah, we are. So 58's out. I have a number, but I usually count wrong. So I'm going to wait to hear from you guys and see if you agree with me. What do you got? 33? That's what I got.
33.
33? Okay, whew, we're happy. 33! So about 33 out of 35? Is that about 94? Percentage-wise? Is that 94%? I'm doing very, very rough Sean math here. 94%, Kevin says yes? Cool. How about this one? We didn't actually calculate this yet, but how about 3 standard deviations? How about 3 standard deviations? We didn't actually calculate this one, but I think you can figure it out. If you needed to calculate what the actual range was, what would you do?
Subtract 16 from negative 47.
16 down from 47 to get down to 63, I guess?
Yeah.
And then 16 up from 17 and go up to 33. We could totally do that if we needed to, right?
Yeah.
How much of the data is in there?
All
of it. All of it's in there. Of this data, all of it's in there, right?
Yeah.
About 100% of the data.
Yeah.
Now, I want to ask you a question that's kind of hard to maybe wrap your head around at this point, although, Candace, what you said earlier makes me think you guys can totally handle it. There's the graph again. There's the graph again. It's bell curve. If I made this bell curve, which is basically shaped kind of like this. Get over there. Suppose we had more variant data. More variant data. In other words, it was even crazier, more varied than the data we just saw. What that would do is it would take the curve and make it wider and not so tall.
Right.
Like that.
Right.
What would that do to the standard deviation, the actual number of the standard deviation? S was 16 in our case. It would be higher, correct? Because it's more deviant data. So these 2 standard deviations, or this 1 standard and this 2, where would they move? they move out. Okay? And if the data was less variant, the bell curve would look more like this, yes? This is a recurring theme we're going to see in this class over and over again, especially at the confidence intervals. And then the standard deviation would move in, which means one standard deviation would crunch in like this. Now that's a bit of a heady thing to go to, but my question is this. Suppose I asked you these questions again. How many are within one standard deviation? How many within two? How many within three? Assuming they're distributed in the same way throughout the bell curve, would those change much? This is a bit of a heady question. What do you think? If I took our black curve and smashed it down and everything moved proportionally, would we still roughly have 23 within one standard deviation?
Yeah.
It seems logical, right?
Yeah.
And you're absolutely correct. It would stay proportional
Just
to
like
that.
changing the scale on a graph.
Yes, it's just like, say that again.
It's just like changing the scale on a graph on your
It's exactly what it is. That's exactly what it is. You're changing the scale. You're shrinking the y-axis and increasing the x scales. The points are staying proportionally where they were. So what's cool about this is, if it happens for one bell curve, it must happen for all of them. Oh, and this is badass. Like, this is totally capital B, capital two S's, badass. When you can say something works for any mathematical entity, you've got power. This goes back to your confidence intervals, 95% confidence, yes? So let's wrap this up in words over here, because this is really, really...